privacy for heterogeneous robot swarms. So heterogeneity is something that we need when we're trying to tackle very complex problems that require a wide range of capabilities. Because our robots, they tend to be constrained at a platform level, we may find ourselves in a situation that we want to distribute these various capabilities amongst our different robot team members. So in order to realize such systems, we actually need to tackle a couple of challenges. The first challenge is, or the first question is, how do we optimally compose our systems in face of trade-offs and costs? The second question is, how do we optimally control a system that is composed of heterogeneous agents? And the third question is, how do we guarantee robustness and resilience in the face of new failure dynamics and new critical links that bring with them certain vulnerabilities? So what kind of vulnerabilities do I actually mean here? So for example, let's assume we have a very important robot type, and that robot type is threatened. So the question of how to protect our systems from those kinds of vulnerabilities really amounts to the question of how do we conceal which robots are important in our system. And I would argue that this is a question of privacy. So what I want to talk about today is how does heterogeneity affect privacy? So let me illustrate this with a bit of a simple example here. So imagine that we have a heterogeneous swarm of robots. Here we have 3 different robot types. We have the blue robot, the green one, and the red one. And these 3 robots are collaborating to solve some underlying problem where they're complementing each other with complementary skills. For instance, they're trying to move an object. At any point in time, we can actually observe the system in its behavioral state. So for example, here we can see that we have groups of robots in 2s and we have groups of robots in 3s. So now let us assume that a malicious outsider can actually observe the system. From the outside, however, all these robots look the same. But the adversary may actually have some side information. For example, he may know which robots are the green ones and which ones are the blue ones. But what he really wants to find out is which one is the red one. So the adversary is now going to try to use the side information to try to find out which this robot is. So this is the problem that we're trying to tackle here. And our approach mainly consists of 2 main elements. So on the one hand side, we have a model of the robot system, and we design a couple of design variables or parameters that allow us to define the system behavior of our robot team. And on the other hand, we have a model of privacy. And the key point here is that the same parameters that allow us to define the behavior of a robot swarm are going to be the ones that influence the loss of privacy. So let me explain a little bit how these 2 elements are interacting. So the key about our robot system model is that we're going to try to model the interdependencies of our different robot types. And the assumption that we're going to make is that the interactions of our different robots can be modeled as discrete stochastic events. So to give you a simple example here, we have 2 robot species that get together to solve a task collaboratively. And any one of these 2 species can be in either one of 2 possible states. So either the robot is searching for a task or waiting for its collaborator to join it, or the robots are together collaborating to solve the task. So the framework that we actually choose to model this kind of system is the chemical reaction network framework. And it's actually quite simple yet powerful framework because it allows us to capture exactly these kinds of interaction dynamics. So on hand of this very simple example here, what our chemical reaction network tells us is that, well, when robots of species 1 and 2 meet, they collaborate to solve the task and then they separate again. And so this reaction actually depends on 2 things. It depends on the number of robots that are available to it on the reactant side, as well as these propensity values, kappa, that essentially together define mass action functions. So the other nice thing about CRNs is that they allow us to track the robot population in these individual robot states. And this is really what I want to talk about next. Essentially, what I want to do is to show you, on hand of this simple example, how the state or the system state is affected by the parameters that define the robot behavior. So let's assume that we have a system that is composed of 4 robots. We have 2 robots of species 1 and 2 robots of species 2. And we can actually model the evolution of this robot system through a continuous Markov chain, where each system state in our Markov chain represents one possible instantiation of our state vector. And the transition rates in our Markov chain are then given by our mass action functions. So in its nominal regime, the distribution of these system states is given by the stationary distribution, which depends on our propensity functions, those kappas. Now let me make a small variation to the system. So I'm going to change something in the database, and I now have robot number 3, which is the species 1. And you can see how by changing the composition of my robot swarm, I'm actually now changing the states that appear in my Markov chain. And this also affects the stationary distribution of my system. And so the key insight here is that, well, if I change the composition of my swarm, I'm changing the states that appear in my Markov chain, and this also affects the stationary distribution of my system. So now I'm going to compare these two systems that I described to you before, side by side. So let's maybe look at the left-hand side plot first. And you'll see the first system that I presented is those are the dark green bar plots, and the second database is the light green. And you can see that for the propensity rate kappa 1, kappa 2 equal, there is actually quite a large disparity, in particular for the first value on my x-axis, which is the state where I have 4 single robots and 0 groups of 2. Now on the right-hand side, I'm actually changing the value kappa 1, which represents the probability of my different robot species to come together and interact. So if I reduce this probability to a very low value, 0.1, you can see that the disparity at the first value on my x-axis, so 4 single robots and 0 groups of 2, is now reduced, so that the probability in this state here is much more similar for both databases. And so the key point here is that by varying the parameters of our system, we can actually control the difference or the disparity of our observable distributions of our system states. And this really leads me to the concept of privacy that I want to introduce today. So what we want to do is we want to prevent the adversary from being able to guess the species of a particular robot. And we do this by ensuring that the disparity of the observable distributions is low enough so that he cannot validate or reject any assumption with high confidence. So in other words, what this essentially means is, how does a single change in my database affect the observable state of my system? So this question has actually been studied pretty rigorously for a while in the domain of differential privacy, which stems from the database literature. And was introduced by Cynthia Dworkin around 2006. And what they defined in their paper was this concept of leakage, which essentially depends on 2 main components. So on the one hand side, we have a database, and the database defines the notion of adjacency. So if I change one element in my database, then that gives me an adjacent database. And the other important element in this formula is that of the query, which essentially is a measurement that is performed on this database and that releases information to the public. So, and what the logarithm in this formula tells me is essentially by how much these 2 distributions deviate. So for very large deviations, this value is actually going to tend to infinity. So now these elements are in place, we actually have to develop an analogy that we can apply to our robot swarms. And so this is how we do it. So our database, as I introduced already before, captures the composition of our robot swarms. Then we have a function that represents the execution of our robot swarm, and we assume that this is a stochastic process. From that, we can derive an internal state at a given point in time. And then we have our query function that reads this internal state and outputs the observable state of our system. So with these elements in place, we can now define what we're calling our differentially private swarm, or what we can also call an epsilon indistinguishable swarm of robots, where the database is capturing the swarm composition, and the query now is essentially this observable or this observation function that gives us the distribution of our swarm over the possible states or configurations. And if this disparity is smaller than the value of epsilon, we're saying, well, our swarm is epsilon indistinguishable. So now the question that arises is, how do we actually compute this distribution here over the observable state? And that will actually depend on what we assume to be our adversarial model. So we've studied 2 possible ways of viewing this. So one possible way to view it is that we have an adversary that can take a snapshot of our system at a specific time t, and that would then amount to solving an ordinary differential equation and solving the system for time t. So where pi is my probability mass function of all the possible configurations that my system can find itself in. And the problem here is that this is a very expensive operation if our state space is large. So at least the people who have been studying this, and one common method to solve these kinds of problems is to use finite state projection methods, where they actually prune the state space, and then the whole evaluation becomes much more feasible. The other way of viewing the problem is by saying, well, our adversary can actually take a snapshot of the system during its operational regime at steady state. And that would amount to finding a solution to this linear system here. This as well is expensive if our state space is large, but we can also find efficient methods for a particular special case. And that is actually the case I want to talk about next, which is complex balanced systems. So if we know that our system is actually complex balanced, then we know that it has a unique steady state, and this the stationary distribution actually has a closed form expression, which will largely facilitate the computation of our leakage function. So it turns out that complex balanced systems are not actually that rare, and what they essentially mean is that the complexes in our systems have equal inflow and outflow. So to recap the example from my early slides, what we see is that a complex is essentially a linear combination of the states on either side of the reaction. And this system here, we can actually represent it through a graph where the vertices are the complexes in our system, and the directed edges here represent the reactions. And then if we can show that we have a reaction rate vector when multiplied by this graph incidence matrix equals to 0, then we can show that the system is complex balanced. And we do that for our previous example, and you can see by studying the very last equation that indeed the inflow and outflow of each complex are equal at steady state. So now recall our formula for the leakage that depends on this probability distribution. And we will now build on a result that was published not so long ago by Anderson and colleagues, which says that the stationary distribution of a complex balanced system is actually a product of Poisson distributions. And then we can manipulate these equations, and we can then formulate a closed form expression for the privacy, for evaluating the privacy of complex balanced forms. And this then only depends on the value xi here, which is the average population in state I at steady state. So now the question is, what kind of systems actually exhibit these complex balance dynamics? So one class of complex balance mechanisms is actually aggregation mechanisms. And I actually like to see aggregation mechanisms as something more general than just the physical coalition kind of aggregation. We could also consider that aggregations happen through targeted communication in a more virtual or abstract space. But the invariant here is that the adversary can observe the aggregate sizes. And so we can actually demonstrate that any aggregation mechanism that can be represented by a directed acyclic graph is actually complex balanced. So now let me show you an actual example of an aggregation mechanism, and then I'll show you a couple of results based on this. So here we have an aggregation mechanism where we have 3 different robot species. Robots of species 1 and 2 aggregate before the robot of species 3 can join. Our internal system state is represented in these 5 states on the right there, and our observable state, or the query, is essentially telling us how many robots are single, how many robots are collaborating in groups of 2, and how many robots are collaborating in groups of 3. And so these results here are showing you the leakage. So the redder it is, the more information is being leaked, the less private it is. And on the left-hand side, what we did was we varied the number of robots that were in either species 1 or species 2. And you can see that we have a minimum leakage value along the diagonal of that plot, which essentially points to the fact that topologically equivalent species, as you can see in the graph up there, they need to be balanced so that we have reduced privacy. And the reason for this is also because there is one single unique way to create this aggregate of 2 robots. So if I change something in the underlying system, so if I remove or add a robot of species 1 or 2, that's going to more dramatically change what my stationary distribution looks like. And what we can also see is that if we increase, more generally, if we increase the number of robots, the privacy tends to increase as well, because we're creating the robots and we're obfuscating the observations. And on the right-hand side, what we're varying is the aggregation rates, And there you can see for larger aggregation rates, we're actually increasing the probability of creating larger aggregates, and hence we're increasing the leakage. So next I'd actually like to generalize these conclusions on larger case studies. And what we did was we actually instantiated, or we formulated this problem as a binary tree. So we're looking at it in an aggregation mechanism that can be represented as a binary tree with 16 different leaf nodes, so 16 different species. And on the left-hand side, we're looking at the leakage as a function of the depth of the tree. So as the depth of the tree increases, we're actually creating more asymmetric aggregation mechanisms, which also means that we have more unique aggregates, and because of that, the leakage is also increasing. On the right-hand side, we're keeping the topologies fixed, but we're varying the rates for a symmetric binary tree representing an aggregation mechanism. And what we can see is that for larger aggregate sizes, we're also increasing the leakage of our systems. So both of these things point to the fact that we're more unique aggregates or more unique coalitions that we have in our systems, the less private our systems tend to be. And so just to summarize these conclusions into maybe a couple of guidelines of how to create more private mechanisms, the first one would be, well, we should try to design balanced aggregation mechanisms, and we can do this by either creating more shallow hierarchies or, for example, by including multiple root nodes. And second, if we really do need unique or large aggregates, then it is better to reduce the interaction time spent in those large aggregates and try to make that as small or as brief as possible. So I'd just like to summarize what I showed you today. So I presented a way of quantifying privacy for heterogeneous teams, and I presented a closed form expression for the special case of complex balanced dynamics. And I showed you how this can be applied to aggregation mechanisms in robust forms. So the next couple of things that I'm really interested in looking at is all of this points to the fact that we want to make heterogeneity less evident in our systems. And that's how we're going to make them more private, more resilient to attacks. And can we do this while we actually maintain the swarm performance at the same time? So with this, I'd like to thank you very much for your attention, and if you have any questions.